Welcome back to the Deep Dive. Today we're looking at something that is a bit of an unsung hero in critical infrastructure.
It's a really important little piece of hardware, even if it doesn't get a lot of attention. We're talking about the NTI E-ACVDRLY-C14 AC voltage
The
detector.
one with the relay, right. And it's essentially an electrical watchdog for those big environmental monitoring systems.
Exactly.
Uh,
For things like the NV or MUX units that you find in data centers, server rooms, that sort of thing. It's just watching the mains voltage.
And its job is simple. It just tells the system alarm or normal.
That's it. It's a very simple, very reliable messenger connected by a basic two-wire cable.
And I noticed the detection range is huge, 50 to 250 VAC.
Hmm.
So you can use it pretty much anywhere in the world.
You can, but the really interesting part isn't just what it detects, it's how it communicates that state without errors.
That's where the internal relay comes in.
That relay is the whole game. It's a simple open or closed contact switch, but the genius is in the engineering, specifically the trip points.
Yeah, I found those thresholds really fascinating, this concept of hysteresis. So the relay closes when it senses voltage going above 60 VAC.
Right. Power's on, the contact closes, everything's normal.
But, and this is the important part, it won't open again until the voltage drops all the way down to 55 VAC, or even lower.
And that 5-volt gap is completely intentional. It's designed specifically to stop the system from what we call flapping or chattering.
So it's not just flipping back and forth with every tiny dip in power.
Exactly. You get these minor, harmless fluctuations on the line, just electrical noise, and the last thing you want is a full-blown system alarm for that.
Okay, so it prioritizes an accurate alert over an instantaneous one.
Precisely. Now, let's talk about how it physically connects to the grid. The C14 model we're looking at uses that universal IEC C14 socket.
Which immediately signals it's for, higher voltage or international applications.
It does. Its counterpart, the E-ACVDRLY-C15, that one has the standard US NEMA 515 plug. But inside, the logic, the relay, it's all identical.
And the electrical limits? They tell a story too. The maximum switching current is only 500 mA.
Right, and that's a key spec. It tells you this device is not a circuit breaker. It is not designed to carry a heavy electrical load.
It's just for signaling.
Purely for signaling. It's a very reliable, very low-power messenger. That's his whole job.
And it's incredibly safe. I was looking at the galvanic isolation 1.5 kV.
Which, for you listening, that's basically an electrical firewall. There's a physical separation between the high-voltage mains and your expensive, sensitive monitoring gear.
So if there's a huge power spike on the line,
It shouldn't get through. It protects your NVI or MUX system from getting fried.
and the reliability figures are just staggering. The MTBF, the mean time between failures, is listed at over 3.5 million hours.
Which works out to something like 400 years of expected service life. Now, that's a statistical model, of course, but it shows you this thing is designed to be installed and then completely forgotten.
Wow. So you put it all together, and what you have is this compact, incredibly high-spec component whose only job is to provide these granular critical status updates.
Exactly. It's there to make sure that when you get an alert about a power loss, it's a real sustained event, not just a flicker.
It's an alert you can trust.
Yep. An actionable alert.
Okay, so let's end with a final thought for you to consider, going back to that hysteresis gap we talked about.
The 55-volt opening, yeah.
So we know it registers a power loss when the voltage drops to 55 VAC. But in some of the technical specs, it notes the closing voltage, the point where it declares power as normal again,
Right.
can be as high as 90 VAC.
Right.
So the question is, why such a big difference? If it's designed to detect a problem at 55 volts, why does it wait for the power to get all the way back up to a stable 90 volts before it gives the all clear? Think about why the engineers would design it to be so quick to raise an alarm, but so cautious, so slow to say that everything is okay again.